Hello and welcome. In the last video on YouTube I presented met glass transformer and demonstrated the circulating power in the secondary coil from a very low power input. I did also highlight that this is achieved by not connecting the cores to each other, but more important, this is achieved by asymmetrical alignment of the cores. In the video today I will replicate it based on ferrite cores. In January 2014 I produced a video on which I demonstrated that asymmetrical alignment of a secondary coil to its primary is resulting in a higher output power. My power source today is a signal generator. We use 10 volts peak to peak. I use an impedance transformer to match the 50 ohms output from the signal generator to the primary coils. This provides a maximum of 1 watt power from a sine wave. This primary has 300 turns with 1 mm copper wire or gauge 18 wire. The skin depth of this wire is 17 kHz. The secondary coil has 550 turns stranded wire. A capacitor is connected in series with the inductor tuned to 15.5 to 60 kHz and configured that resistance and reactance allows for the phase angle of voltage and current close to be zero. The measurement is displayed in watts, but this is a measurement of circulating power between charge and discharge of the capacitor. There is no work performed in a classical sense except the production of a very large magnetic field. I measure electrostatic and magnetic fields and do coil alignment in real time. A walkthrough video is taken with no cuts for you to see my demonstration setup and the test. I will after the video create a poll for you to vote if you like me to do the same test as a streaming event where you witness and operate the circuit, and to make a test with an LCR meter to learn more of the core design and the parameters. Let us have a look now at the demonstration table. So here you see the setup for today. So in the center you see the 3 ferrite cores. They are 5 and 6 centimeter long. The center of the core, but it's 10 centimeter ferrite rods, standard ferrite rods you can buy for AM amplifier. Right and left are the 300 turns primary coils with 1 mm wire, and we have the stranded wire with 550 turns in the center. So technically both primary operating in again in half bridge way, zero switching technically, but both cores or both primaries together have more windings than the secondary coil. However, only one at a time is activated, so there is a slight amplification of voltage based on the turns between primary and secondary. So the toroid core here is the core I used before. This was specifically for Tesla coils, where I have the possibility to match impedance up from 50 ohms up and from 50 ohms going down. And I had various tabs in there. However, because of this core material is 3C90, it is not well suited to have a high fidelity of square waves at frequency of that low of 15 kHz or lower. Therefore, I would need to produce a new core based on nanocrystals where I have high fidelity even down to 1 kHz, reproducing a square wave as a pure and clean square wave. That is here not the case. I have to go over 100 kHz to demonstrate that. However, we are working on sine wave, and in sine wave it's working fine. So we have then my spectrum analyzer where I measure magnetic fields here only, and the magnetic fields in the room is around 200 milliampere per meter. We will start that. I have the signal generator switched off currently. On the right hand side you see 2 static meters. One which shows simply the polarity, and the small one, the black one, shows red and blue for either negative or for positive. and it also registers the energy fluctuation from 50 Hertz. So we have definitely 50 Hertz from the room in the coils, but at a very low margin, but this one can measure it. The more expensive one, which can go up to 20 kilovolt, will show that much more in detail, that we have technically almost no voltage, so there is no electrostatic voltage there. So I will go over now to the demonstration table and start with the walkthrough from my GoPro to the signal generator, where I will position it, and we will start everything from scratch, and we do the test before we do energize anything at all. Let's do that now. As I said, we're starting with a walkthrough that I see how I set it up here. I have part of my equipment, which is up here, camera. Here I have my large oscilloscope, and the smaller one is here. We have connected the differential probe here, current probe here, and an additional voltage probe on that side. Let's go down here. So we have only one power connection. Black cable goes up to the signal generator. There is nothing here underneath, if that's even relevant, but the purpose of this video is, as I said, to show the asymmetrical alignment and the power it produces when doing in a correct fashion. So I will keep this here, and I switch over now to the composition. We do that all in live. So you should see that now. Yes, it's okay. So we have currently nothing connected, and I start up here. This is indicating just high voltage static electricity, and it always comes up with blue. Blue means negative. I zero it out and I can go around, and when I come close to the coils, you can see here it measures 50 Hertz. I zero it out, it measures 50 Hertz, but also when I go to this here, it measures 50 Hertz on my hand. It goes to 0, there's nothing. Here we have nothing, and here on the table, here we have some areas, nothing, but from underneath, so we have nothing. I switch this one off, and we go further and we do a test here. I zero it out now. Now we can measure. It focuses in, it measures about the 40-50 volt static electricity. It's not nothing. Here we have 0. Here nothing. Let's see here where it complained. Now it measures 50, 60, 70 volt. And the GoPro does not show anything. So we have no electrostatic energy here in the field. Now let's start up the signal generator. So we start it up. Before I configure that one, I want to have the measurement here of our current in the room. 178 milliampere per meter. I measure in 3D. I measure with 0 dB. That means we have no amplification. That is the room. That's what the current, what the whole room has. And it goes a little bit higher up on the ceiling. 189. If I go to the coil, see what that makes, what difference that makes. 177, even lower. 176, so they all show the same values. 187, and the ferrite, if the ferrite shows anything. 174, not much. Right, so the first thing we're gonna do is we're changing the voltage to 10 volt peak to peak. So if you see that, we have 5 volt plus and we have 5 volt minus equals 10 volt peak to peak is RMS about around 7 volt, and 50 ohm, as you can see here, 50 ohm as the output gives you a maximum of 1 watt at this energy. We have the coils currently directly connected as you would do, and I keep the meter on here at the moment, and we can measure here the taps as well. So let's start that. Now we go to the frequency of 50 kilohertz. Let's have it like that. I will energize now. I have some loose connection. I don't know where it actually is, so I need to find that, but just to make you aware that it can happen. So I tune that in, and this is the maximum we can get currently from systems. It measures 18.9 ampere currently. That is by directly connecting the coils. 20 ampere. We go over here. It measures 36 amperes, and we measure over here. Measures 29 ampere. And in the further distance, let's say we go here. It measures 1.5 ampere. So it's quite dramatically how that dissipates, right? We can keep it back here. So now, in order now, and take note at the frequency, we are at 13.1 kilohertz when they're directly connected. That means the frequency is lower. I start slowly only with the first primary to remove that slightly out, and I adjust the frequency. Now I go with the secondary out and adjust the frequency and see if we can add anything here from the coil here. Let's have a look what we have here. On this coil is correct. Set it. Amplitude again is correct. 10 volt peak to peak. Setting here needs to be correct. It was set to 100. Need to set it to 10. It was too low, so let's do that again. So we're here currently. So you see the distance here between here and here. Let's have it like that. I should normally achieve a value of 100. Very important. The current probe picks up the magnetic field here, but also picks up the magnetic field from this coil. It is not really relevant because I'm not measuring really power we are using. I'm measuring the magnetic field strength, and as you can see here, I measure here at the moment 23 ampere per meter, and if I go over here now to this side, 47. So we have on a primary a larger side, but we have also solid wire here, and we have stranded wire here. So there's more copper wire here technically on that wire, which dampens actually the magnetic field. 47. Let's go over there. We have here 32. Go a bit closer. 36. Let's see if I can fine tune that. I'm currently at 60. I should be able to get that up to 80. See if I go further in, move that coil a little bit, so I can adjust then the way it measures it. Here we go. I'm at 80 and I measure now 49 ampere here and change this a little bit. So that's 82 watt currently. From a magnetic influence we have 49 ampere per meter now. I go back here, 25. Let's see, let it run through another time. Now it stays by 25. Let's go over there. It's 29. $28, $29, yes, stays here, and again here. 7. Now let's do some quick electrostatic. If there's any electrostatic energy in here, it has, need to zero it out. Let's see here. It has not changed, so there is no electrostatic, it's purely electromagnetic. Here I'm on 0, and here nothing is happening here. So we have no electrostatic fields in here anywhere, only electromagnetic fields. So we are still at, we are at 83 at 84 watt. And see if I can make some more changes. $84 watt, that's the best thing I can do currently. $85. This is only the alignment, that is very important. It's all about how you align them, and they are not connected, and if you take the gap distance between both of them, there is a ratio between them, and I believe if it's a golden mean ratio, it would be best, because if I go out here, if I'm outside of the golden mean ratio, it's not good anymore. If I go too close, it's not good either anymore. It has to be, as you see, if I pull that out, at the Goldilocks position, it's perfect. Now that is sine wave, we know that, and we know that this core cannot produce probably square wave. So, but I can put it in here, it will still get higher. You would see we would have under square wave, if it would be perfect square wave, I would definitely be over 140, 150 watt here as a display from a magnetic field. But if I look now, how much current do we have, or but how strong is the magnetic field? Let's have a look now. We have here 50 ampere. $26 ampere also, again, very low, so you should be able to see that. Sorry, yeah. Now let's go here. And here I measure 46. So we have technically on that side the strongest radiation. Let's do that again. 47, is that correct? You need to get it running through again. So if I go at the end, where we have normally the magnetic field exposed going to the outside, look at that. We have very, very little coming out here on that side. Even if I go very close, 26, sorry. If I go here on this side, I measure here, I measure 5, let's do that again, let it run a bit. Here it measures 20. Here it measures 11. And here again, it's not super accurate what I'm doing here, 11 as well. And if I go here in between, 72. So we have a very strong magnetic field radiation from these fields out here, and that makes an impact. The coils itself radiate, of course, but it comes mainly from the cores here at the exposed area where they don't connect. If I go directly to the coil here in the center, it should drop quite a lot. Oh, it says 51, maybe I'm too close. 41, let's do it here again. I'm fairly close now. I wasn't so close before. 62, and here 47. So it would take a lot of information. We would have to write that down, do statistics, measure the distance between the coil cores and so on, and do a charting to plot down actually the performance of the different measurements, is a different distance and so on. That's what I've done 10 years ago with this bipolar Tesla coil, where I used then, instead of fixed capacitance, I used fluorescent light bulbs as capacitance, and I could measure then with my current probes the power going through together with the voltage I measured at each side. So we measure the voltage here as well, we see that. So we have here 153 volt currently. These are all RMS values, very important. There are no peak to peak, all RMS. So I think that is a good starting point, and if you like to do that for me in a streaming or online session, please vote for it. If I get enough votes, I will perform it, and then I can disconnect the cables. We can some measurements. And here I want to show you the how much voltage do we have coming out from the system. It's the blue line. Because a square wave, let me change it to sine wave. So 1.9 volt, 1.9 volt comes out, and you can see if I go to the individual tabs here, 13 volt, 11 volt, 17 volt. So I have, for each individual tab, I have the possibility to match then exactly the impedance I require. So that should be good for now. Digest that, go through the video a couple of times, and if you're interested that I do that live for you in a session and see what you would like to do some tests, we can do that all live. I put my LCR meter and take the coil out. We make different changes, wiring and so on, and that should be a great thing where you can learn something without building it yourself. Thanks for watching, and until the next time.